Somewhere beneath the ancient cratered floor of the largest impact scar in the entire solar system, there is material that was never supposed to reach the surface. Not lunar dust, not ordinary crust. Rock torn directly from deep inside the moon itself, blasted upward by a collision so violent it happened before most of the solar system's planets had even finished forming. For decades, scientists knew this material was theoretically down. There somewhere. They just didn't know where or how much, or whether astronauts could actually reach it. In June 2026, two newly published studies finally answered those questions, and the answer landed directly on top of the exact region where NASA's Artemis astronauts are now scheduled to walk. Tonight, we're looking at what researchers actually found buried beneath the moon's south pole, how a team of scientists managed to reconstruct a 4-billion-year-old collision in stunning detail, and why this discovery is now shaping exactly where humanity's next moonwalkers will step. To understand why this matters, you first have to understand exactly what astronauts are heading toward. The South Pole Aitken Basin is the largest confirmed impact basin anywhere in the solar system, a colossal, elongated scar stretching across a huge portion of the moon's far side, so large it dwarfs anything comparable on Mercury, Mars, or even Earth. It's also the oldest major structure on the lunar surface, meaning whatever formed it happened extraordinarily early in solar system history, back when the moon itself was still a young, geologically active world. NASA has now selected 9 candidate landing regions for its upcoming crewed lunar landings, and every single one of them sits on the rim of, or immediately outside, this ancient basin. Sites like Nobel Rim 1, Nobel Rim 2, and Hayworth fall directly within the basin's boundary. Malapert Massif sits near its rim. De Gerlache Rim 2 lies just outside it. The reasons for choosing this general region are practical ones. Astronauts actually need to survive. Nearby water ice locked in permanently shadowed craters, and long stretches of sunlight for generating power. But the basin itself, the reason it exists at all, remained a genuine scientific mystery right up until this year. It's worth appreciating just how significant a landmark this basin actually is, even before factoring in any of the new research. At roughly 2,500 kilometers across, it's not simply the largest crater on the moon, it's one of the largest confirmed impact structures anywhere in the solar system, full stop. A scar so immense that its outline is difficult to fully appreciate from the ground, and only becomes truly comprehensible when mapped from orbit. For a mission planning to send astronauts to the lunar surface for the first time in over half a century, choosing to land directly in and around a structure this ancient and this scientifically significant wasn't a coincidence. It was a deliberate decision to put the next generation of moonwalkers in direct contact with some of the oldest, most revealing geology anywhere within reach of human exploration. That mystery is exactly what two newly published research teams set out to solve. One study, published in the journal Science Advances on May 6, 2026, and led by Shigeru Wakita at Purdue University, focused on reconstructing the original impact itself using advanced computer simulations. The second, published in JGR Planets on April 23, 2026, and led by Gabriel Gauman at the University of Arizona, focused on mapping exactly where the debris from that impact actually ended up using high-resolution gravity data. Together, with William Bodka of the Southwest Research Institute serving as a co-author on both papers, the two studies gave scientists their clearest picture yet of what's actually sitting beneath the ground Artemis astronauts are about to walk on. Wakita's simulation work revealed something researchers hadn't fully appreciated before. By recreating the ancient collision digitally, testing different impact angles, speeds, and compositions, until the simulation finally produced a basin matching the elongated, lopsided shape we actually observe today, the team determined that the object responsible struck the moon from the north, at a notably low, glancing angle rather than a direct head-on hit. That low angle explains why the basin stretches out instead of forming a simple circular crater. But the more striking discovery was about the impactor itself. According to the simulation, the object that created this basin wasn't a simple uniform chunk of rock the way most asteroids are. It appears to have been differentiated, meaning it had a distinct internal structure, a core surrounded by layers of separate material, more closely resembling a small protoplanet, one of the early building blocks of planet formation, than an ordinary asteroid. As Wakita put it, the simulation didn't just reproduce the basin's shape. It revealed details about the nature of the object that created it and the direction it came from, information scientists had been trying to pin down for decades. That distinction between an ordinary asteroid and a differentiated protoplanet matters more than it might initially seem. A simple, uniform asteroid strikes a surface and produces relatively predictable, homogeneous debris. A differentiated body, with a distinct core and separate outer layers, behaves very differently on impact. and the composition of what it leaves behind on the surface depends heavily on exactly how deep the impact reached into each of those internal layers. Confirming that this specific impactor had that kind of internal structure gives researchers a far more detailed picture of not just what hit the moon, but what kind of material that collision would have actually delivered to the surface. Information that feeds directly into predicting where the most scientifically valuable debris is likely to be found today. When an object like that slams into a planetary surface, the destruction goes far deeper than an ordinary impact. The collision that formed the South Pole Aitken Basin melted rock directly at the point of impact and blasted material outward from far beneath the moon's surface, well past the thin outer crust and into the mantle, the thick, dense layer of rock sitting directly underneath it. That's the material scientists have been hunting for ever since. Genuine, verified, mantle rock, sitting exposed on the lunar surface, something astronauts could never obtain by digging a hole with ordinary equipment, but that this ancient, violent impact effectively delivered to the surface on its own 4 billion years ago. That's where Gaumann's gravity mapping study comes in, and it's the piece that turns this from an interesting historical reconstruction into something directly relevant to the Artemis missions themselves. Using high-resolution gravity data gathered by NASA's GRAIL mission, combined with detailed models incorporating both crustal and mantle material, Gaumann's team worked out exactly how that ancient, ejected material likely settled across the basin and the region surrounding it. Their conclusion? The basin very likely contains a substantial deposit of genuine lunar mantle rock, mixed throughout the debris blanket surrounding the impact site. In some cases, carried even further by smaller secondary impacts that scattered material even closer toward the south polar region. As Gaumann explained, the precise distribution of that mantle material had remained a significant unknown for years, but the team's models now indicate the original impact ejected enough deep material to form a genuinely accessible deposit, some of which, at trace levels, may exist directly within the regions currently being considered for Artemis landings. Sit with what that actually means. Scientists had previously assumed the deepest, most scientifically valuable ejected material would likely sit far from any realistic landing zone, tucked away in some inaccessible stretch of the basin astronauts would have no practical way to reach. This new research suggests otherwise. Some of that ancient mantle material may lie close enough to the actual candidate landing sites that future Artemis astronauts could plausibly collect and return samples of it, genuine rock from deep inside the moon, material that has never before been directly available to study, all without requiring any specialized deep drilling equipment. It would effectively be a 4 billion-year-old geological gift, already sitting on the surface, delivered by the same catastrophic impact that carved out the basin in the first place. To put that in perspective, every single sample humanity has ever collected from the moon, from the Apollo missions through China's more recent Chang'e efforts, has come from the lunar crust, the relatively thin outer shell of rock sitting on top of everything else. Nobody has ever held a confirmed, verified piece of the lunar mantle in their hands. It's the equivalent of studying an entire planet for over half a century using only samples scraped from its outermost skin, never once getting a direct look at what's actually underneath. If Artemis astronauts really can collect genuine mantle material during a South Pole landing, it would represent an entirely new category of lunar sample, unlocking direct chemical and mineralogical answers to questions about the moon's interior that scientists have only ever been able to approach indirectly through gravity measurements, seismic data, and computer models like the ones behind this year's 2 studies. This isn't a purely academic curiosity either. Understanding the moon's earliest history helps scientists understand the early history of the entire solar system, since the moon, unlike Earth, has no active plate tectonics or weather erosion constantly erasing its geological past. A rock sample pulled from deep inside the moon and preserved essentially untouched for 4 billion years offers a direct window into a period of solar system history that's almost completely erased everywhere else, including on Earth itself. But to summarize the stakes plainly, the basin offers scientists a genuinely rare opportunity to study the moon's earliest history, precisely because the impact was violent enough to excavate material from deep inside the moon that would otherwise remain permanently out of reach. This research also builds on discoveries that came before it. Back in 2019, scientists identified an unusually dense, likely metallic mass buried beneath the South Pole Aitken Basin, a hidden structure roughly 5 times. Larger than Hawaii's Big Island, its exact origin still debated. And in June 2024, China's Chang'e 6 mission successfully landed within the Apollo Basin, a smaller crater sitting inside the larger South Pole Aitken region, becoming the first mission in history to collect and return samples from the lunar far side, samples scientists are still actively analyzing today. Each of these findings adds another piece to the puzzle Artemis astronauts are now walking directly into. What makes 2026 such a pivotal year for this story is the timing. These findings didn't emerge as some abstract academic exercise, years removed from any practical application. They arrived just as NASA has finalized its short list of candidate landing sites, all clustered in and around this exact basin. And just months after the Artemis II crew, flying past the moon in April 2026, captured their own images of the basin's heavily cratered eastern edge from orbit. A real, current glimpse of the very terrain scientists are now mapping in unprecedented geological detail. The science and the mission planning are, for the first time, developing in direct conversation with each other. So, when future Artemis astronauts finally step onto the lunar surface near the South Pole, they won't simply be walking across ordinary lunar regolith. According to this year's research, they may be standing on top of, or very near, fragments of the moon's own mantle, material blasted up from deep inside the moon by a violent ancient collision billions of years before anyone existed to witness it, waiting patiently on the surface for someone to finally arrive and recognize it for what it actually is. Every step across that ancient basin floor will effectively be a step across a 4-billion-year-old crime scene, one that scientists have only just now finished, reconstructing well enough to know exactly what evidence might still be lying in plain sight. If you want to be here when Artemis astronauts finally collect the first confirmed samples of lunar mantle material, subscribe and turn on notifications. Because after 4 billion years buried beneath the surface, this ancient rock may finally be about to tell us where it's been.